This video is going to be over problem 4.11. We're going to be looking at calculating entrance dose and exit dose from parallel opposed equally weighted beams. Okay, so for problem 4.11, we're going to be giving 120 monitor units through each field in the treatment delivered in the previous problem, which if you've seen before, if you watch the video on that, you know pretty much how that one worked out. So the question here, rather than delivering a specific dose to this midplane, we're looking at delivering 120 monitor units through each field, and we're going to determine what the dose is at first at mid depth and then at Dmax of either of the two parallel opposed fields. Since both fields are going to be using a 4MV, and they're going to be cutting through the same material, this one is not going to be too bad of a problem for us to work through. So let's take a look here. At what we're going to need. So let's take a look here at part A. So for part A, we know that we have 120 monitor units, and we're going to be looking at the dose at mid depth. Now, if you'll remember the equation, we're going to have dose delivered to whatever point we're looking at, and then we're going to have our rate. So we're going to have the centigrade per minute, or in this particular case, since we're dealing with an accelerator, this is the centigrade per monitor unit, basically the calibration factor. That is going to be multiplied by the area factor. I could spell that like a human being here. Let's see. And then that is going to be multiplied by the PDD. This is all going to be equal to the number of monitor units. Now, in this particular case, in the previous problem, we were trying to figure out what the monitor units are going to be. This time we're actually given that, and we've got to figure out what the dose is. So the dose in this particular case is going to be equal to the monitor units times the centigrade per monitor unit times area factor times the PDD. So the dose at midplane, we know that the monitor units are going to be 120. We know that the dose rate is going to be 1.0 centigrade per monitor unit. We know that the area factor is going to be 1.022. We know all of this because it's spelled out here. There's an area factor. We know what the reference centigrade per monitor unit is. And then we need to know what the PDD. If you remember back from this particular problem, you know that the PDD in this particular case, and I'm going to have to turn this off for just a second. The PDD in this particular case was gathered from this part of the table there in 8.2. I went through in that previous example and figured out what it was at 10.5, and then tried to calibrate that for a 13 by 13 field, which was in between the 12 and the 15, which this was the 12, this was the 15 at 10.5, and this is approximately what it would be at the 13, so 59.85. So now let's go back here. I'll start up annotation again. So that gives us 59.85. Now, again, I'm going to take that and make that into a decimal. So it'll actually be 0.5985. So the dose, if I take all of those numbers and multiply them together, and I'm going to go to the calculator here. And I'm going to take 120, multiply it by 1, which is just that, and multiply that by 1.022, and then multiply that by 59.85, and then divide that by 100 to change it into a decimal. So I end up with 73.4. And that's how many centigrade I have. Now, that's for one beam. Since I have two beams, the amount of dose is actually going to be, and I'm just going to put this down here, dose for both beams is going to be equal to 73.4 centigrade times 2. So 73 times 4 is going to be 146.8 centigrade, or if I ask you to round it, it would be 147 centigrade. That's at midplane, where the dose that's being contributed from the anterior and the posterior are going to end up being the same. So you got our patient here. So you got the AP beam, and then you've got the PA beam. And at midplane, they're both affected by the same depth. So the dose that they're contributing here is going to be the same. Now, the next step is going to be a little bit different. At the next step, we're going to be looking at something here. We're going to be looking at a different point. This is going to be Dmax. Dmax, things work a little bit, well, I mean, things work the same. But what you have to remember here is that the PDD is going to be different in each case. Now, I could look at the front and 1 cm in, because that's going to be your maximum depth here for 4MV. So you could look at 1 cm in, or from the anterior, or you can look at it from the posterior. It doesn't matter. You'll come up with the same answer either way. So let's go to our equation again. And let's say this is going to be at D max. So let's say for the AP beam. Earlier, I didn't have to specify because I was going to come up with the same calculation either way. But if I'm looking at an AP beam, then I know the dose is going to be equal to 1.0. Let me back up just a little bit. It's going to be 120 MUs times 1.0 centigrade per monitor unit. So that means those two units cancel. Times 1.022. Now, what might the PDD be in this case? The PDD, since we're at D max, is going to be 1. So the dose in this particular case is just going to be this times this times this times this. So 120 multiplied, clear all of this out, 120 multiplied by 1.022 is 122.64. Now, that's just for the AP beam. For the PA beam, we're going to be looking at 120 MU times 1.0 centigrade per monitor unit times 1.022 times, now here's the PDD. What is the PDD, and what depth are we looking at? The patient's chest is 21 cm. If I'm looking at a point here, D max, that is 1 centimeter in from the anterior, that means it is 21 minus 1 coming in from this direction, or 20. If I go here and if I look, and this is the column here for the 12 by 12, this is the column for the 15 by 15. If I interpolate, basically go a third of the way from 32.5 over to 33.8, I'll save you a little time here. You come up with 32.9333. So let's go back here. And so right there, I'm going to be adding in and I'm just going to put it down here, 32.9333. And of course, that gets changed to a decimal. So I end up with PA dose is equal to 120 MU times 1 times 1.022 times 0.3293. Doing all of that. Let's see if I can activate it. I can't do it. Okay. So I get 120 times 1, which is just going to be 1 times 1.022 times 0.329333. Throw in 3 of those for good measure. So I come up with 40.389. Equal to 40.389. So if I add 40.389 to 122.64, what do I come up with? Because both are contributing to dose at that particular point, come up with a total dose of 163. Okay. All right. That's this problem, and I will continue to work others as we go through this section.